Okay, here is a quick look at the Altair Embed eDrives model for driving the Texas Instruments F280049C coupled. That's on a launch pad coupled with the Boost XL 3-phase gallium nitride inverter board. So here we're looking at the top level of this diagram. This is what we call the source code diagram, and it contains all the blocks needed to do the control. It's got some pre-scaling, it's got some output. We can simulate this, but we don't have a plant model for the motor here, but you've seen there's other diagrams for that. This one we're going to compile, and then we'll go into a debug diagram and watch the motor run and see how we can change parameters and look at the motor waveforms while it runs. So let's drill into the controller. And this is the first layer that we see coming into the controller. And the light blue blocks are what we call compound blocks. Those are blocks that contain other blocks. And it's strictly a visual technique to reduce clutter. There's nothing about being contained in these blocks that alters the execution order. However, you see two other blocks with a green diagonal and a red diagonal. Those are telling us that those compound blocks, they also contain blocks, but they're going to be executed at different rates. The red diagonal, if we control right mouse, we see that it is executing on an interrupt, and the interrupt is the ADC B interrupt. And if we click on the select button, we see it's the end of conversion 3. Sorry, end of conversion 2. And it starts with the conversion 0, so there's 3 elements that it's going to convert, and there's 2 elements on the other 2 ADC units, so it's going to do a total of 7 3-phase, 3 voltage, and the DC bus. The green diagonal is interesting. That one is executing at a fixed rate of 0.01 seconds, 100 hertz, and it's going to code gen as a background thread. What that means is it's not triggered by an interrupt, so it suffers jitter. It's preempted by any interrupt task, base task, and it runs it's scheduled out of the idle loop. So low overhead stuff goes in there. This is some startup housekeeping. There's a couple timers. We wait for the inverter to get to stable voltage. Then we zero our ADCs, and then finally we enable the control. So let's drill into the main motor control that's activated on our ADC interrupt. And at this level, we see the main controller in yellow. There's a field weakening side controller to generate the ID value, and it decides when it makes sense to kick the field weakening in. This is calculating instantaneous power, which we can read out interactively or make decisions on. And then we see this block here on the far left is the encoder angle module. That is the one piece that's target specific to the 280049. And likewise, this block contains the PWM. Let's drill in. And it also contains the ADCs. And when the ADCs come out, there we see the voltages and the currents, and we do a Clark transform on both the currents and the voltages. Here's the 3 PWMs, one for each of the 3 phases. The way the launch pad is configured, the way TI decided to do it, the 3 PWMs are numbered 3, 5, and 6. Not exactly what you might expect, but that's how TI chose to do it. If we look at these PWM blocks, which are part of the standard target support that Embed provides for TI, we can see that it lets you choose any kind of rate scaling, the count mode, is it up, down, the timer period, it's running at 20 kilohertz. We're running our torque loop at 10 kilohertz, so you can see down here we're sending the ADC startup conversion pulse divided by 2. So we're dividing that 20 kilohertz in 2. However, when we look at our utilization of the MCU, we'll see that we could actually do it at 20 kilohertz if we wanted to. I didn't create this diagram, so I don't know the rationale for having done it at 10 kilohertz. But better to have extra CPU to do that than not have enough. And for the ADC unit in here, we see here's the actual ADC register reads, all on the left. And then you see there's ADC offset corrections that are the compound blocks that are executing. Whoop, a little bit off screen there. What that's doing is a slight filter while it's in zeroing mode. And what happens is when the part first boots up, it sets all the PWMs locked at 50% duty cycle. So phase to phase, there should be no relative voltage difference. Whatever the voltage is on that channel, we call that 0. So when the motor's running, if it's above that voltage, is a positive current or voltage. Anything below would be a negative voltage or current. And as I mentioned, those are Clark transforms. So the alpha betas for the currents are fed into our current controller. The voltages we're just using for our power calculator. The voltages would be used for a sensorless controller, and that will be talked about in another session. So here is our speed controller. That one's running at a different rate. You see those green diagonals? We're running that at a kilohertz, so 10 times slower than our torque controller. Here's the reference speed compared to the shaft frequency. It's going to do a difference. We apply the KPKI. That's going to end up with an IQ ref. And the IQ and the ID reference are going to be fed into the core current controller. Notice there's current ramps here. They are essentially rate limiters that are going to prevent sudden discontinuous changes from coming through. So anytime those parameters change, there are limits to how fast that change can happen, so they smoothly move from one change set point to the next. And the rate of that is set in the user parameters block. So if we drill into the current controller, here's our forward park, and then we do a KPKI. Our PI controller is done on the error, the D and the Q error, and we come with the D and the Q out, and those D and Q outs are then sent into an inverse park along with our sine and cosine, and we do an inverse Clark with the third harmonic, and those are our 3 PWM signals that at this point they're plus minus 1, and they do have to be massaged into 0 to 1, but that's fairly straightforward. And that was done back in the PWM block. Here is the generation of our sine cosine, and we're actually, for purposes of experimentation and development, we have a open loop ramp driven angle that we take sine and cosine of, and then we have a theta that we're getting from the quadrature encoder, so that when we want to run full field-oriented control closed loop, we'll close the loop around the position read from the quadrature encoder. Oh, and then we have a speed estimator here from the sine and cosine signals. So here is their encoder module. We drill in. This is the actual block that corresponds to the hardware encoder on the C2000, and we let you get at all the settings, and you can graphically select how you want to configure it. So it's set up to reset on each occurrence of an index event. It's on unit 2. There's several units here, and we always, every peripheral lets you choose which PWM pin you want to use for that peripheral, and the pin settings here are the ones available to us on the TI Launchpad. So that covers all the blocks. And there's one more interesting block here, the diagnostic tool. If we go in there, this is letting us write data to multiple monitor buffer writes. So you can see in this case we're storing 901 words, and it automatically takes the data type. These are 16-bit scale ints coming in, and we actually give you a choice. Each buffer can be a choice of two things, and we're going to look at phase currents or phase voltages basically. And while you're debugging, you might want to look at different things as well. But the idea behind this buffer is it runs at the full rate of the diagram. So if we look down here, the diagram's running at 10 kilohertz because we're inside that interrupt handler. And the buffer fills at that 10 kilohertz rate. So whatever signal you want to look at, that is sampled at very regular intervals at whatever speed you're running at. And then once it's filled, the PC running Altair Embed has a monitor buffer read that then can reach in, grab that buffer, and put it into a vector plot. So it gives you a digital scope, which is very handy when you're doing things like motor drives. Okay, so that's the source code. So to compile it, you just let me move the little thing there. Yeah, okay, tools. Oh, give me a break. So what I'm going to do is do a right button and compile it. Okay. And that generates the code, runs it through the C compiler, and links it into an out file. Boom. Done. And then that out file, because let me see how to move this frickin' thing. There's a little floaty thing. Okay. Let me just go back to the CodeGen dialog. If you go to the dialog, oh, interesting. Good, I did that. What you have to do, I remember now, in order to debug, you have to select the block that you want to compile that will take all the inputs and allow you during your debug session to change the values interactively on the inputs, and it'll take all the outputs and let you plot them or display them, what have you. That's in addition to the monitor buffers I spoke of earlier. So let's recompile that. See, now this is checked to use the edge pens for data exchange. That's how we do debugging, and we'll compile that. So the C compiler is chewing on it. This is TI's compiler. Okay, got our out file. So now let's go to the debug diagram. And this is this block here is a target interface block. It's preloaded to the path of the out file on the hard drive. So when we hit the go button, the first thing this block does is download that out file and set up a handshake to allow interactive communication of these inputs, so we can turn on and off various aspects of the controller, see how it behaves, and we can look at things like the bus voltage, the rotor speed, that kind of thing. CPU utilization, I mentioned that earlier, we can look at that. Also, here's the monitor buffer reads that read that buffer data that was down on the target, and it'll plot it here in a digital scope. So this trigger is true every time there's fresh data. That gets right in. So let's go ahead and hit the go button. Oh, and by the way, we're set to run it here at 1200 RPM. If we look over here, it looks like in the meter in the upper right corner, we're about at 1200 RPM. In fact, up here, we're at 12,896, 1201 RPM. Yeah, pretty good. At watts, we're burning about 3 watts. It looks like our supply of DC amps is running about 0.18 amps, I would say. Full scale, it's 2 amps, so it's below 0.2 amps right there. And our torque is millinewton meters. We're running about 10 millinewton meters. Now, what I can do, I can pick the motor up. You can hear the little bit of tape flying around. I can slow the motor down. I can speed it up. We can turn on field weakening, and you can hear the motor speed up a little bit. It's off. So without field weakening, we're at about 2,000 RPM. Bump it up, we're starting to get to 24. So we get a couple hundred RPM out of it. But if you look, you can see the watts jump up to almost 16 watts, turn it off for almost 8 watts. So double the power for not much speed increase, so you really got to need that speed increase. Maybe you're in your Tesla and you want to win a drag race or something. Okay, so there you go. This is showing off our hardware in the loop interface. And you have seen how to create firmware for a permanent magnet synchronous motor using Altair Embed eDrives. Thank you very much.